So a little while ago, I made a video talking about the differences between text and binary serialization. Two of the kind of possible ways that we can take data and put it into a format that ultimately we can transport in one way or the other. Commonly to a file or through the network or into a buffer of memory. I'll have it linked up there. If you haven't seen that video, I recommend you watch it before watching this one. Because today we're going to take a look at the specifics. How do we actually serialize data in Hazel, my game engine? And more specifically, I'm not going to talk about text serialization today. We're specifically going to focus on binary serialization. Ones and zeros. Exciting. Okay, so the name of the game with Hazel, and I've mentioned this before, but I just want to mention it again, is simplicity. For those of you who don't know, a game engine and making games with a game engine is a lot of work. I mean, like, a lot of work. And really the only way that it's possible to try and make anything of real substance with a small team or even by yourself, if you're making a game engine, is to keep things simple. I'm a big believer that lots of things are very, very over-engineered, and in a lot of cases, they just simply don't need to be. And I think part of the problem when you're engineering software is always about like knowing the context. So the best solution generally is going to be the most simple solution. I can probably just say that across the board. The best solution is the simplest solution, providing, of course, it satisfies all of your requirements. And the reason why that blanket statement works so well is because no one ever desires something more complicated than it needs to be if the end result is the same. And there's seemingly no benefit to having something more complicated, right? The simplest solution is always the best solution. And so when I'm developing Hazel, that's something that I commonly think about. How can I make this as simple as possible whilst fitting our requirements? And that, I think, is really the key. What are our requirements? We are not some AAA game engine that has to generically suit any kind of genre or graphical style of game out there. That's just not who we are, and if we were trying to do that, I don't think we'd get very far with the extremely limited resources that we have. Instead, let's focus on baby steps. Let's try and get a system up and running. Let's have it satisfy all of our immediate requirements in the simplest, easiest to understand possible way. And then if we need to build on that, if we need to iterate on that, well, we can, because software is quite mutable. We can always change things and potentially make them a little bit more complicated with the benefit of meeting new requirements, obviously, when that time actually comes. So the reason why I felt like discussing that was because I feel like serialization is a topic that can get extremely complicated. And I'm specifically talking about the implementation, especially in a language like C++, because C++ doesn't have a built-in reflection library, at least not at the moment. And what that basically means is our ability to almost like in a meta way, look at the code and see what the code itself is saying rather than what it compiles into, because that would enable us, for example, to just take an object or a struct of data in C++, and no matter what those underlying types are, no matter how the data is actually stored behind the scenes, we can kind of automatically process that and write like a more or less generic way to convert that into that byte stream that we're looking for binary serialization. That's easily achievable in a language such as C#, for example, which has all of this built in, because C# is a much kind of higher level language in the sense that it sits on top of like a runtime environment, and it's not as like bare bones compared with C++, especially if we are specifically not trying to use all of the features of C++. And so because C++ doesn't have this like natural reflection ability, it's very common for people to try and add that using the preprocessor and like templates and macros. And there are lots of different implementations of reflection in C++. I'll leave some links in the description below if you do want to take a look at them. But as someone who has dealt with systems like these professionally at EA on their core technology, I made the decision pretty early on in Hazel that I specifically don't want to do that. And it's not because those systems are bad. It's just that the amount of engineering effort that is required to, first of all, like write that system or integrate an existing one, ensure that it works with everything else, and then most importantly, debug it, as well as teach the rest of the engineers on the team and future volunteers and everyone else how it works and what to do if things go wrong, and how we can even, again, debug problems that can happen with that system. I just made the decision that this team is just not at that level of like resources available, basically, where I want to spend any time on that. And instead, I opted for the much simpler solution of like, you can't just auto-magically write out objects or structs or more complex like data structures and types and all of that we might have within Hazel's core systems. You can't just simply write them out auto-magically. You have to actually sit down, spend a little bit of time to be like, okay, how do I want to serialize this and how do I want to deserialize this? But the benefit is that you know exactly how it works. You can step through it line by line. There's never any like, wait, what's happening behind the scenes? Because you're not behind the scenes, you're in the scene. So again, not saying that necessarily like all those reflection, auto magic stuff is bad. I'm just saying that I've decided to go for a more manual approach that, you know, in all fairness, we could probably spend some time automating bits of it, like partially. But the real benefit here is that I think it's really, really easy for everyone to understand. I don't think anyone watching this video, hopefully with the way I explain it, will struggle too much to understand how this works and how they can basically use it to serialize any data you might have inside C++, really. Anything that you have should be relatively straightforward to actually get down onto disk or into a memory stream or into the network. Now, before we continue, I want to mention that if you guys are just starting programming and you want a really good, interactive, engaging way to learn the basics, as well as brush up on your math of all levels, then Brilliant.org currently has a 30-day free trial that you can use to check out their entire platform for free. Brilliant.org/Cherno, link in the description. Let me tell you about what Brilliant is. Brilliant.org is an amazing website filled with lots and lots of really high quality courses on various STEM topics. As I mentioned, computer science, if you're just starting, Brilliant.org will teach you like all of the basics of how to think like a programmer, which is really the most important thing in the beginning. And the reason why I specifically think they're a good idea is because their courses are super engaging and interactive. Instead of just sitting back, zoning out, watching videos, you actually have to engage with this content. Like for example, learning about this logic here. You'll have to actually put the pieces together and make sure you understand how it works. And then you can actually start putting that into practice by taking a look at some of their Python courses in which you'll actually write like working Python applications. And while you're doing all of that, don't forget about math. Math is so important for programming, and Brilliant.org starts all the way down at the beginning with the everyday math course and goes all the way up to things like calculus. Again, with this interactive, engaging way of teaching, these widgets you can play with to see how numbers work and how everything works visually, which I think is the best way to learn. And as I mentioned, they have a 30-day free trial that you can use to take a look at all of these courses. Just go to brilliant.org/thecherno, link will be in the description below. And if you do go on to like it, then that link will also get you 20% off an annual premium subscription. Huge thank you as always to Brilliant.org for sponsoring this video. All right, enough talk, let's take a look at some code. I just really wanted to emphasize that simplicity is beautiful. Keep things simple. Let's take a look at the code. Surprise, no code, it's blank. That's because it doesn't exist. No, I'm joking, of course it exists. I wanted to instead draw you guys some pretty high quality diagrams. I don't know why I'm doing this here and not using like that, what did I, Excalidraw or whatever? I like using that tool. I'm just gonna show you this drawn thing instead. So basically, I've already messed this up, but I'm gonna keep going. There's two sides to this binary serialization, obviously. There's the writing and there's the reading. Usually I like to write the writer first, because then you can read the data that you've written back in. Because writing, I guess, is where you actually potentially conjure up some data, you make up some data, and then you actually write it to disk, for example, or you write it to the network, or you write it to a memory stream. I think from now on, we're just gonna assume that we're writing to disk, okay? Reading and writing to disk is like what we're doing today. So once I've written something that writes data to disk, I will write something that reads data from disk. In both cases, I'm writing the code, but I'm writing a writer and then I'm writing a reader. Confused yet? Did I mention this would be simple? So that's really step one, I think. There's just this distinction between like, you have a writer and you have a reader. Step two is, what are you writing to and where are you reading from? Is it a file on disk, as I mentioned, or is it, you know, the network? Is it a memory stream? Because this same concept of writing and reading data can be applied to different like specific implementations, what I like to do is basically make like an interface or like an abstract class, like a pure virtual class called something like stream writer. And obviously all of this stuff is, there's a parallel to it, which is the reader component. So this, I'm gonna draw the writer component because as I mentioned, I like doing that first, but picture that there's also a reader. And so stream writer, what is that responsible for? The idea of a stream writer is it will write data to a particular stream. That's it. What kind of stream is it? Is it a memory stream? Is it like a file stream? Doesn't matter, it doesn't know, it is just a collection of functions that have no implementation that you from an API point of view don't really need to care about whether or not you're writing to memory or to disk. You're just like, hey, stream writer, write me some bytes. The implementation then decides what it's actually doing. So then over here, we might have a file stream writer and a memory stream writer. Aren't you glad that I didn't go with diagramming software? And these specific classes, by the way, these are all classes. So we have a stream writer class and then we have two subclasses that implement the functions defined by this interface. These two subclasses, they will provide those specific implementations, whether it be for a file stream, you're writing to a file, or you're writing to just to a buffer in memory. Okay, so let's take a look at some code. Here it is, been here the whole time. So here's this stream writer. And as you can see, these are just pure virtual functions here. I don't know if we actually have any, no, we don't have any like members or anything. It's just an interface ultimately. And again, this is specifically the writer. We also have the reader component, which I can put over here. And they are largely parallel, meaning that like, you know, we have the same functions in like all of them. It's just that like we have write data here, but we have read data over here. Before we get into how we actually write data and everything, I can also show you those implementations that I talked about. So like the file, I think it's just called file stream over here. So this is the file stream writer and reader. They're actually in the same file that's just called file stream. You can see it derives from that interface and then it implements all of the functions that it needs to that are relevant to this specific type of writer. And the reader, yeah, kind of does the same thing. You can see how simple this looks so far. I can also quickly show you the memory stream version, which is memory stream writer and reader. You can see that it just has an actual buffer that it writes into. Buffer in Hazel is just like a wrapper around data and a size, along with some like lots of functions to deal with that data. But essentially it's like a non-owning wrapper around a pointer, which greatly simplifies lots of operations to do with buffers. But otherwise the memory stream writer implements all these functions. The reader implements all the functions. Same situation, just different targets. Essentially, one is a file and it will use like, you know, OF stream, output file stream, input file stream, whilst the other will just use basically a pointer in memory, which is the buffer. Now, speaking of simplicity, yeah, we're just using C++ standard library file operations here. I think there are some things in Hazel's file system that are like operating system specific. So we would use like the Win32 API in this case. Obviously, we try and use the portable C++ library as much as possible. If there's a specific reason not to, either it's like too slow or there are just functions or things that we want to run that is not supported, does not exist in the API, then we'll go back to the operating system API. But generally, I obviously recommend that everyone uses the C++ library until you have a reason not to, just because it gives you so much more support for different operating systems, different platforms, just out of the box without you having to do anything. Which again, if you're on a resource limited team, very, very important, very valued. So in the case of the file stream writer, let's take a look at, yeah, how this works. I mean, it's really simple. We basically create an instance of this with a path. It will open that out in binary like format. It'll close it on the destructor. So we're using a bit of RAII here to just kind of maintain the lifetime of the stream, and then write data will simply write data. Isn't that crazy? This is the entire implementation. This is all we have. So then how do we actually write stuff? Because this obviously just writes like a pointer. It seems like it would be kind of useless. Well, the cool thing about this, I think, is that everything basically just comes down to this function called write data. And same for the reader. It all comes down to this read data function, which will just read from the stream, which is again, C++ standard library API. The real magic of like making our lives easier happens in the actual stream writer, which is the interface. And the reason why is because there are lots of different functions that will, at the end of the day, just call this write data, which again is not implemented in this particular class because it's dependent on the implementation, the specific implementation, but it still lets us ultimately do what we want with the pointer data, basically get the data we need as like a stream somewhat, so that we can then put it into this write data function, which is just the most simple way that we deal with data, which is a pointer and a size. That's really all data is. That's what is in our memory. We have lots of different memory addresses of different locations that will contain data that we care about. And of course, then we have a size so that we know, well, how big is that data and where does it end? This is where it starts. We add size to the pointer. That's where it ends. So then everything else is just a wrapper around that. And specifically, you can see we have something like write raw, which that's really easy. It's templated so that we can put anything in there and we can just write like whatever raw data we might have, like an integer, for example, a struct. We would use write raw for that. Write object is for more advanced kind of non-trivial types. So this is where we might have something that we can't simply grab the memory of, in which case you can see it will actually try and call a static function called serialize on the actual object, right? On the object type with the instance that we're trying to serialize, as well as the current instance of our writer, which basically means that it's then up to that class, that object, to define how step by step it gets serialized. That's where the whole manual situation comes in, because for basically everything else, it can more or less be automatic, but if you have like these non-trivial types, not just like a straightforward buffer in memory that you just need to get to disk or to memory or whatever, then you actually have to spend some time implementing all of that. And I think a good example of that is our shader system, actually, because we have lots of different shader reflection pieces of information that we need to serialize into like a shader pack so that we can, anyway, lots of reasons why, but if we take a look at this, like don't worry about the fact that this is like Falcon code or whatever. This is just a struct of data, right? But it's a bit non-trivial, mostly I think because it has this string here. So what we do is we have a static void called serialize, which again takes in that stream writer as well as the instance of this class that we're trying to serialize. And you can see what it does. It just goes through and it's like, yep, write this stuff as raw because it's just bytes. And then write this string as a string because a string is a special type. This is a C++ string. If we take a look at what that does, write string, you can see all it does is it just writes the size first. So we have a 64-bit unsigned integer, which is the size, and then it grabs the data and obviously like the length of the data and it writes that down. And then for the deserialization, same exact situation. So it's kind of easy to visually see whether or not you've got this in the same order. If you mess this up, yeah, you're gonna get errors. It's not gonna work. Again, that's where this whole manual component comes into it. But ultimately read raw will just read data. So if we go to like file stream, it will just read and that's it. It will return true. There's no way to even return false here. We probably should do a little bit more like, you know, error handling and being a bit safer with all of this. But hey, resource limited, this is what we put together. This is what I threw together, I think in time for like asset packs, for like the Ludum Dead, I don't know, dichotomy. All the way back when we made dichotomy, we had to ship some code. This is what I threw together and I don't think I've worked on it since. So yeah, lots of room for improvement, but it works. That's what we currently have. Coming down to some more like data structures. So like write map and write array. So array might be a little bit easier. So what this will do is it will go through. So this any kind of type of array you might have. An array, by the way, is just a vector. In this case, you pass in a vector of any type. There's a little boolean here for whether or not you actually want to write the size as a uint32t in this case for some reason. And then we iterate through every element of that vector. And then if it's trivial, then we will write raw, right? So if it's just a struct of data, if it's just an integer, you know, we don't have to write it as an object and go through that custom like serialize and deserialize function. We'll just write it raw. We'll just write the bytes. But otherwise, if it's not, and we're just using const expert here to just do it kind of at compile time. If it's not, we'll write it as an object, which will go back and actually call that serialize function that we talked about just then. So element by element, we just write all that down. For a map, you can imagine it's going to go the same way. The only difference is that, well, in this case, I think we have a custom template specialization here for string specifically. So if the key is a string, we don't have to like worry about writing it as an object or whatever. We can just write the string and then write the value of the map, either raw or as an object. And then if we have a situation where the key is like a different type, then obviously we can go through, check to see if the key is trivial or not, write it raw or object, value, same situation, raw or object, and the size is optionally written. I think stream reader is going to do the exact same thing. So we take in a map by reference here, which is our target where we write to, and then we'll go through, we'll grab like the key, we'll read it raw or object, same with the value, and we'll just store that directly in the map that we're trying to read here. And if the size that we pass in is not given into this function, so we don't know how many elements to iterate through, we assume that it's inside that serialized stream and we'll try and read it from there. That is pretty much all there is to it. I hope that makes sense. Let me show you some examples. So I think asset packs are probably like the juiciest example. So we have this class here called asset pack serializer, which just basically will serialize like an asset pack and also deserialize its index so that we can actually see like what assets are within that asset pack and then decide to like load whichever ones we need. So over here, you can see we create a file stream writer. So this is that class that we looked at earlier. We're creating an instance of it just on the stack like that. We've called it serializer, and it's going to have this path that we're trying to write the asset pack to. The first thing we do here is we write raw this asset pack file header. Now this is ultimately an optional template parameter because it can obviously be deduced from the actual type, but it just makes the code a little bit more clear because we can see that we're writing this specific struct just as a raw stream of bytes. And the reason we can do that is because file header, you can see, only has this, right? It's just got some characters over here, a UN32T, a UN64T. It's obviously a trivial type, so we can just write that raw. Then this is a little bit more complicated because we actually have to like basically make room for an index, but we have to write the index later because the index will contain offsets of each asset and we haven't written each asset yet. So for example, we might have like a 3D mesh at byte offset, 500,000. We don't know that it's going to be at 500,000 yet when we write this index. So we have to write like these placeholder zeros to advance the stream forward. And then we'll actually jump back. So we have this current stream position as the index position. We'll actually end up jumping back later over here so that we can actually get those like, binary offsets and everything and the index written. Anyway, this isn't going to be specifically a video about how asset packs are serialized. I more just want to show you how the API works. If we scroll down to deserialize index, then we can see like the reverse of this, right? So we have a file stream reader instead of a writer with that path. And then we'll just go ahead and try and read that file header as just raw bytes. So file header, this is obviously passed in by reference so that we can actually write directly to it. And it will just deserialize those bytes right into this memory. We do have some safety checking just to make sure that we have that magic bytes at the beginning of the file to identify this as a proper Hazel asset pack file, as well as some version checking. And then, we'll just go through and do read raw. So it's exactly like the reverse of this. That's the other thing you obviously have to do manually with this system. You have to make sure that everything is mirrored. All of your write then has read, and it all works like it's supposed to. So that example may have been a little bit complicated because it's an actual real world example of us using it. So instead, let me show you the simplest thing I can, which is how would we write something like this from scratch? So if we wanted to write something, again, we would begin with a file stream writer to write to disk. I'll just call this stream. We would pass in a path. So like example.bin, it is a binary file. And then into here, we can just be like, I want to write a string and the string is hello. And that's cool. If we had like, I don't know, a struct of data, which, had like, let's say UN8T called A, which was 5, B, which was, 2. I'm hoping to read this later. We might have our data instance over here and we want to write that. So in that case, we would do write raw and we just pass in data and that would actually work fine. If we wanted to, we could also specify type as a template parameter to make it more clear. If we had a struct that was slightly less trivial, NT data, non-trivial data, that might have like maybe like a pointer to like an array or something. Let's just say buffer equals new UN32T. Maybe it's like an array or a buffer of 4 of these integers. That obviously we can't, we could still write that raw, non-trivial data. We could still try and write that raw, but then what's gonna happen is it's actually gonna go through and write the memory address of this pointer and not the actual contents of it, which is what we want. So instead, what we would do in this scenario is we'd actually put in a static void serialize. And if I go over here to where we were, just so I can copy this. Once we've got that, we would have to implement it manually like so. So this would be write raw, A, write raw B, and of course this has to be relevant to the instance, which is not uniform buffer, it's NT data, and these are not arrows. And then for this buffer, we could just do something like write buffer. And this is a Hazel buffer, but you can make a Hazel buffer from just a raw pointer. The only addition that we need to obviously provide is the size. So in this case, this would be like size of UN32T times 4, and this has to be relative to that object instance. So we would do that. And then we would implement a deserialization function, which would basically, again, be mirrored. So instead, we would do deserializer and then read raw. And then for read buffer, because this wants a Hazel buffer, which we could have just made that a Hazel buffer, but anyway, this is getting a little bit messy, but we could wrap that buffer pointer in this and then pass that in without a size this time, right? So this doesn't actually need to have an allocation or anything, because write buffer will actually write the size of the buffer into the binary file. And this is basically what we would have. So then to actually write it, we would do stream write object this time, and the object would be our NT data. So we would do that instead of that. And again, if you want, you can specify the template parameter. So that's basically the serialization side of things. The writing, the reading is going to be very, very similar. Again, just read instead of write. And then obviously we want to be able to store this somewhere. So let's just say our string over here. We'll see if we can read back some of this stuff. I might put this over here And then we'll also have target objects to read over here. And let's just do a little debug break and let me try and actually run this. So I put this into runtime layer for some reason. So let's stick it in the constructor. Then I just need to make sure that, yeah, sure. Let's just run this. Also put the prototype for the function here, and let's see if this runs. Okay, so there's our debug break. So let's inspect these objects. So here's our string. You can see our string says hello. I realize this is probably a bit of a dumb test because obviously we have the default values here. So therefore, if we try and inspect this, I'm sure we'll get the right data. But if we take a look quickly at our working directory, then here's our example.bin file. Let's take a look at it in HXD, and you can see that we have, what did we write first anyway? So our first thing was us writing the string hello. So if we take a look at it, so hello starts over here because the first 8 bytes are the size, right? So we have like a uint64t 8-byte unsigned integer holding the size. So the size is 5 because there's 5 characters. Then we have the characters hello, and then, you know, we have that 5, 2, and then that array or whatever. This array we just wrote out as a buffer, and the buffer is going to be 4 times 4 bytes. So that's why we have 10 over here. 10 in hexadecimal is 16. And then we have a whole bunch of CDs because, well, we never set the memory for this. This was just uninitialized debug memory. Now, if we just, as a quick little dumb test, let's just take away all of this. We won't do this writing either. We'll just try to read it. Let's see if we can get those values that we just deleted back. And if we take a look at data, there's 5 and 2, there's 5 and 2 in our, probably our uninitialized memory buffer, as well as that string that we requested over here. Okay, so that's serialization in Hazel. Really simple, does the job, works. There are many more things to be desired. I don't mind this manual way of doing things. As I mentioned, yes, it's a bit annoying. Yes, it's a bit error prone, but it's dead simple. It works really well. And every change you make to it is more or less explicit, which I like. I'm more concerned about the general safety of this, because if stuff does go wrong, you'll generally just get like either memory corruption or like, you know, just crashes because you're writing or reading things that don't make sense. Like for example, if something shifts and then you read the size of an array and turns out instead of 5, it's like, you know, a uint32t, like close to uint32t max, or like it's just like some garbagely high number, and then you try and read that much of the file, you're obviously going to crash. Like stuff like that, we need to add a bit more defense to. And then, you know, I mean, if we were really serious, I guess endianness is something to consider as well. I'm actually not sure if the C++ library gives you much consideration, because remember, we are using that specifically. Oh, actually, one more thing that I didn't show you is if we wanted this instead, so let's get rid of this if false. If we wanted this instead to be written to a memory stream instead, we could just make this a memory stream writer and a memory stream reader. So if we go up over here, we just have to make sure we include that. So instead of this being like this, what we would do is we would have like our memory stream as a buffer. We would pass that in with some sort of size that we need to know. I'm gonna say like 50, and everything else stays exactly the same. So over here, I would supply this memory stream instead. And that's basically it. It's exactly the same. It's just the type. It's just that implementation type that makes all of the difference. Anyway, I hope you guys enjoyed this look at Hazel's serialization situation. Is this the way it's gonna stay forever? I don't know, probably not. But let me tell you, after dealing with automagic systems not working very well, this is a little bit refreshing. And because we can kind of get away with it at this scale, yeah, I'm gonna try and get away with it. Let me know what your thoughts were in the description below. Don't forget that you can get access to Hazel by going to patreon.com/thecherno, or you can go to get.hazelengine.com. Your support is what makes Hazel possible in the first place, and you'll get access to all the source code. You can take a look at this serialization implementation in practice with all of the code, as well as even use Hazel and make games and whatever you want with it. If you have any more topics you want me to cover, let me know in the comment section below, and I'll see you guys next time. Goodbye.